Pluto is, on average, about 5.9 billion kilometers from the Sun. Light from the Sun takes 5.5 hours to reach its icy plains. It took New Horizons 9 years to get there, traveling past Jupiter's orbit, beyond Neptune, and into a darkness that, in our imagination, seemed almost endless. Yet when it flew past Pluto in 2015, there was no wall ahead, no final road sign, and no boundary marked end of the solar system. Instead, beyond Pluto lie countless icy worlds. Further out are shards of ice held in the Sun's gravitational pull, massive plasma bubbles that pulsate with the solar wind, and a shell of comets that has never been directly photographed, but may extend more than 1 light-year. The solar system we saw in our textbooks as children depicted the planets lined up in a row, with Pluto at the very end. That illustration wasn't wrong. It simply depicted only the opening act of a vast story. Tonight, we'll set out from Pluto, traveling through the Kuiper Belt, the solar wind termination shock, the heliopause, and the Oort Cloud, in search of the true edge of the solar system. Along the way, we'll discover a counterintuitive fact. The solar system has no single definitive end. If you measure it by the planets, the answer lies beyond Neptune. If you measure it by the solar wind, the answer lies more than 100 astronomical units away. If you measure it by the Sun's gravitational influence, the answer extends as far as nearly half the distance to the nearest star. If you enjoy this kind of cosmic journey, be sure to like and subscribe. Get ready. Let's begin. Let's return to Pluto itself. It is not a failed planet banished to the gates of the solar system, but rather evidence that has made humanity realize our maps were wrong. After its discovery in 1930, it was long classified as the 9th planet. It has ice caps, mountains, a tenuous atmosphere, and a massive moon, Karen. Its world is complex enough that it resembles a true planet, even more than many of the blurry specks of light observed through early telescopes. The problem wasn't that Pluto was too small, it was that it wasn't alone. In the early 21st century, astronomers discovered an increasing number of massive icy bodies beyond Neptune, some of which were close in mass to Pluto, and one, later named Eris, was even slightly more massive than Pluto. If Pluto were still a planet, then there were many other members in the same region that would equally qualify for the list. The classification system could no longer pretend that this was just a single special exception. In 2006, the International Astronomical Union added a new criterion for planets. A celestial body must not only orbit the Sun and be nearly spherical, but also dominate its orbital neighborhood. Earth and Jupiter meet this criterion, having long since cleared, absorbed, or ejected the large debris surrounding their orbits. Pluto does not. It shares a crowded, icy region with a vast number of Kuiper Belt objects, and was therefore reclassified as a dwarf planet. This controversy led many to believe that Pluto had been demoted. In fact, it has gained a more significant status. It is no longer a lonely last planet, but rather the first inhabitant of a new realm. Just like the first island discovered off a coast, what truly matters is not which flag flies on the island, but the realization that an entire archipelago lies beyond it. Pluto has a diameter of about 2,377 kilometers, making it even smaller than the Moon. But small does not mean simple. Together with Charon, it forms an extremely unique binary system. Charon is large enough that their shared center of mass lies outside Pluto's surface. They are not a giant body accompanied by a small moon, but rather two tidally locked dance partners, forever facing each other with the same side. Pluto also has smaller moons, such as Nix, Hydra, Charon, and Styx. The entire system resembles a family of fragments left behind by a massive early collision. Pluto's seasons are not like Earth's 4 seasons. Its axial tilt is very steep, and its orbit is highly elliptical. One Pluto year is equivalent to 248 Earth years. When it is close to the Sun, nitrogen, methane, and carbon monoxide ice on the surface sublimate, forming a thin atmosphere. When it is far from the Sun, these gases condense back to the surface. Pluto's atmosphere is not a stable blanket enveloping the planet, but rather a thin mist that slowly breathes in sync with its long orbital period. The blue haze captured by New Horizons was particularly surprising. Ultraviolet radiation from the Sun breaks down methane in Pluto's atmosphere, generating complex organic molecules high in the atmosphere that gradually settle to the surface, possibly giving some regions a reddish-brown hue. That distant ice plain is not a pure white, lifeless world. It has chemical cycles, seasons, and evolving terrain. Though the Sun is far away, its influence is still sufficient to keep this tiny dwarf planet complex. Neptune's average orbital distance is about 30 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, approximately 150 million kilometers. The Kuiper Belt beyond Neptune extends from about 30 astronomical units to near 50 astronomical units, forming a flattened icy disk around the Sun. This is not a hollow abyss, but a region of extremely cold leftover building material, preserving fragments that were not formed into planets during the birth of the solar system. In this region, water ice is as hard as rock, nitrogen and methane condense into frost, and the Sun is merely an exceptionally bright star. The temperature on Pluto's heart-shaped nitrogen ice plain is as low as nearly minus 230 degrees Celsius. Gases that would boil on Earth can lie on the ground there, forming a thin layer of seasonal frost. The solar system does not end at Neptune. It simply transitions from a world of rock and gas to a world of ice and darkness. The orbits of the Kuiper Belt objects also tell us that this region has never been a quiet warehouse. For every 2 orbits Pluto makes around the Sun, Neptune completes exactly 3. This stable relationship is called a 3-to-2 orbital resonance. The two will never collide, because every time Pluto approaches Neptune's orbit, Neptune is in a different position. The gravity of the giant planets acts like an invisible hand, continuously organizing, compressing, and protecting the orbits of distant small bodies over billions of years. This resonance is no minor detail. It records a long migration that took place in the early solar system. The planets did not necessarily form in their current positions. Numerical models show that Jupiter, Saturn, Uranus, and Neptune exchanged angular momentum with the gas disk and countless planetesimals around the young Sun, causing their orbits to shift slowly. As Neptune migrated outward, it swept through the outer debris field like a plow, dragging some bodies into resonance while flinging others into extreme orbits. Pluto is thus like a preserved fossil. Its orbit is tilted and eccentric, and it does not follow the neat, nearly circular formation of the 8 major planets. It tells us that the early solar system was not the smooth, stable, textbook-perfect structure we see today. Back then, planets were moving, ice bodies were colliding, and massive gravitational disturbances flung primordial material in all directions. The order we see today is the calm that remains after a cosmic scale collision. When the solar system was born, the young sun was surrounded by a disk of gas and dust. In the high-temperature region near the sun, only heat-resistant rocks and metals could condense, eventually forming Mercury, Venus, Earth, and Mars. Further out, as temperatures dropped, volatiles such as water, ammonia, and methane could freeze, causing a sudden increase in solid material. This allowed massive cores to grow rapidly, capturing the surrounding hydrogen and helium gas to form giant planets like Jupiter and Saturn. Beyond Neptune, the primordial disk still contained a large number of icy planetesimals. They collided and merged with one another. Some grew to the size of Pluto, while others were flung into more distant orbits by the gravity of the giant planets. Jupiter's influence was particularly intense. It acted like a massive gravitational slingshot, flinging many nearby celestial bodies out of the solar system and sending others into extremely elongated elliptical orbits. Without the early perturbations caused by Jupiter and Saturn, today's Kuiper Belt and Oort Cloud would likely look completely different. This process also explains why the total mass of the Kuiper Belt is much smaller than expected. To produce large bodies like Pluto at distances of several dozen astronomical units, the primordial region likely needed far more solid material than exists today. However, Neptune's migration, the scattering of the giant planets, and prolonged collisions cleared away most of that mass. What we see today is a plundered ice reservoir, with insufficient remaining material to easily reconstruct its original scale. Before New Horizons reached Pluto, many people assumed it was nothing more than a cratered, long-frozen, lifeless ball of rock. The images transmitted by the probe overturned this expectation. Water ice mountains rising thousands of meters high, plains with few impact craters, flowing nitrogen ice glaciers, and a blue atmosphere with a thin haze. Billions of kilometers from the Sun, geological activity has not completely fallen dormant. That famous heart-shaped region, officially named Sputnik Planitia, covers an area nearly the size of a large country. It is composed of nitrogen ice, which can still convect slowly at extremely low temperatures, like a pot of thick liquid that never boils but constantly stirs. Warmer ice rises from the depths, cools and sinks back to the surface, gradually smoothing out old impact craters. Pluto lacks Earth's oceans and volcanoes, yet it possesses its own slow weather and glacial cycles. Pluto's secrets did not end with the flyby. New Horizons continued outward, passing the minor body Arrokoth in 2019. Located about 44 astronomical units away, it resembles two snowmen joined together. The two parts of Arrokoth are gently fused at an extremely low speed, having been scarcely altered by violent impacts or internal heating. It is like a speck of dust preserved from the solar system's infancy to the present day. The existence of Arrokoth reveals that the solar system did not begin with planets, nor does it end with them. Every major planet is composed of countless smaller particles that coalesced, while the Kuiper Belt preserves those unfinished building blocks. They have orbited the Sun here for more than 4 billion years, like bricks forgotten in a corner of a cosmic construction site. Pluto is not the end. It is merely our first true step into this construction site. There is another particularly important detail about Arrokoth. Its two lobes did not merge through a violent collision, but rather seem to have gently pressed together after a low-speed encounter. Such a contact binary supports a scenario for the formation of the solar system in which dust and small particles can first gather gently in locally dense regions and then gradually merge, without having to undergo collisions akin to high-speed car crashes at every stage. A small icy body, located as far as 44 astronomical units away, is helping scientists look back at how planets first formed. The Kuiper Belt also contains many small, deep red objects. Organic compounds on their surfaces have been gradually transformed by cosmic rays and the sun's ultraviolet radiation over long periods, forming complex dark red substances. Every color, every binary system, and every resonant orbit is like a fingerprint left by different eras. These objects are too small to reshape themselves through internal thermal activity, as planets do, so they preserve their orbital history from over 4 billion years ago in their surfaces and motion patterns. Not all outer solar system objects remain neatly within the classical Kuiper Belt. The orbits of scattered disk members can be repeatedly tugged by Neptune. Their perihelia sometimes approach Neptune, while their aphelia can be flung as far as 100 astronomical units or even farther. They are like vehicles kicked off a busy planetary highway. They still occasionally pass by their old exits, but they are already heading toward uncharted distances. The scattered disk serves as a dynamic corridor between the planetary system and the more distant realms. But the Kuiper Belt is not the final layer. It thins out around 50 astronomical units, a region astronomers sometimes call the Kuiper Belt's cliff. It is not that the sun's gravity suddenly vanishes, but rather that the distribution of primordial debris, Neptune's migration, and long-term collisions have collectively shaped a drop in density. Looking only at this layer of the disk, one might think the edge has already been reached. Then, some objects begin to appear in much more distant and peculiar orbits. The most famous of these is Sedna. With a perihelion of about 76 astronomical units, it lies far beyond Neptune and the classical Kuiper Belt. At its farthest point, it is more than 900 astronomical units from the Sun. It takes approximately 11,000 years to complete one orbit around the Sun. The last time Sedna was near its current position, humans had not yet built cities, and many prehistoric civilizations had not even emerged. What is most unsettling about Sedna is not its distance, but the fact that its orbit defies easy explanation. It is too far from Neptune for Neptune alone to have pushed it onto such a path. Yet it is not so far away as to follow the nearly random trajectories typical of Oort Cloud comets. It seems caught between two worlds, partly belonging to the planetary system and partly already influenced by the broader galactic environment. Later discoveries of stray objects, such as 2012 VP113, also exhibit similar anomalies. Their perihelions lie far from Neptune, as if they had been flung out of the chaotic gravitational zone of the planets by some ancient force. Possible explanations include the Sun forming early on in a crowded star cluster, with neighboring stars once passing close by. It could also be a complex consequence of the migration of the giant planets. And some have proposed that an as-yet undiscovered giant planet is slowly shaping them from farther out. The early star cluster hypothesis paints a very intuitive picture. The Sun did not necessarily form alone in today's quiet region of the Milky Way, but may have resided within a cloud of gas alongside hundreds or even thousands of other young stars. Those stars were much closer to one another than they are today. When a neighboring star swept past the outer reaches of the solar system, it did not need to penetrate Neptune's orbit. A single, gentle, and prolonged gravitational tug from a sufficient distance would have been enough to send some icy bodies into an isolated orbit like Sedna's. If this scenario is correct, Sedna is not a mysterious exception, but rather an old photograph from the Sun's birthplace. Its orbit preserves a chapter of history that humanity will never be able to witness firsthand. The Sun once had closer neighbors, and the light of young stars once simultaneously illuminated the surrounding protoplanetary disk. Later, the star cluster dispersed, leaving behind only stars scattered in different directions across the Milky Way today, along with a group of distant icy bodies in anomalous orbits. The ninth planet hypothesis, on the other hand, offers a completely different narrative. If a massive hidden planet were to exist, it would, over an extremely long period of time, use its faint gravitational pull to gradually alter the perihelion direction and orbital inclination of distant small bodies. It would not disrupt the surrounding world as conspicuously as Jupiter does, but rather act like a distant hand, making slight adjustments with each orbit, revealing the overall pattern only after billions of years. The problem is that the discovery of distant celestial bodies is inherently biased. Telescopes are more likely to detect faint, small objects during certain seasons in certain regions of the sky and at certain orbital positions. The fact that a small number of objects appear to point in the same direction may reflect a real gravitational structure, or it may simply mean that we have been searching in the same patch of sky all along. Science should not treat a hypothesis as a fact lurking in the darkness, simply because an explanation is dramatic enough. The search for Planet 9 remains an ongoing endeavor. This hypothetical ninth planet easily brings to mind a new Pluto-like story. If it exists, it might have several Earth masses and orbit the Sun along an extremely elongated elliptical path, hundreds of astronomical units away. But it has not yet been directly observed, and the clustering of distant small bodies may be influenced by observational biases and sample size. It is a hypothesis worth pursuing, not a known planet already hiding in the darkness. Regardless of whether the ninth planet is ultimately discovered, Sedna has proven one thing. Depicting the solar system as 8 planets plus a ringed belt is far from sufficient. The region beyond Neptune is not a flat wasteland, but a set of overlapping dynamical regions. Resonant objects, scattered disk objects, out-of-band objects, and dwarf planets all move along different orbits, with each category preserving distinct scars from the early solar system. Beyond these icy worlds, the journey enters another kind of boundary. It is defined not by rock, ice, or planets, but by a stream of charged particles continuously emanating from the Sun. This stream is called the solar wind. The Sun's outer atmosphere constantly hurls protons, electrons, and a small number of heavier ions in all directions at speeds of up to hundreds of kilometers per second. It is invisible, yet it travels farther than any planetary orbit. The solar wind is no ordinary wind. On Earth, wind moves leaves because air molecules collide densely with objects. The particles of the solar wind are so sparse that a person immersed in it would not feel a breeze. But it carries a magnetic field and momentum, continuously expanding and pushing out a massive bubble into interstellar space. This bubble is called the heliosphere. It envelops all the planets and most of the Kuiper Belt, and also shields the inner solar system from some of the high-energy cosmic rays coming from the Milky Way. The solar wind originates in the Sun's outermost layer, the corona, where temperatures reach millions of degrees. There, searing plasma escapes outward along the Sun's magnetic field lines. Some of it bursts out at high speeds from regions with more open magnetic fields, while other portions flow out more slowly from more complex magnetic structures. It is not a steady fountain. Sunspots, solar flares, coronal mass ejections, and magnetic field reversals all alter its speed, density, and direction, causing the entire heliosphere to feel the effects of changes on the Sun's surface, with a delay ranging from months to years. Near Earth, the solar wind typically travels at several hundred kilometers per second. It collides with Earth's magnetic field, compressing the magnetic tail on the day side and stretching it on the night side, creating auroras, geomagnetic storms, and the space weather that satellites must contend with. Outward toward Jupiter, the solar wind still interacts with Jupiter's massive magnetic field. By the time it reaches the vicinity of Pluto, though much thinner, it remains the dominant background in that region of space. Only much farther out does the galactic counterpressure finally bring it to a halt. The Sun's magnetic field is also dragged along by this wind as it rotates. Because of the Sun's rotation, the magnetic field lines do not radiate outward in straight lines, but coil into a giant Archimedean spiral, much like the curved water trails drawn by a rotating sprinkler on a lawn. Planets, comets, and charged particles all exist within this invisible network of magnetic fields. What we see are the orbits of the 8 planets, but what truly weaves the space within the solar system together is this constantly oscillating electromagnetic web. Imagine the Sun as a spring at the bottom of the ocean. It continuously spouts a luminous stream of water outward. The flow is strong at close range, spreads out as it moves farther away, and eventually encounters back pressure from the surrounding seawater. The heliosphere is the bubble formed by this stream of water as it swells in the ocean of the Milky Way. It is not a perfect sphere, because the solar system is traveling through the nearby interstellar medium at a speed of tens of kilometers per second. The side facing the wind is compressed, while the leeward side may be stretched, twisted, or even split into complex tails. All the planets are sheltered within this bubble. Earth is only 1 astronomical unit from the Sun, where the solar wind remains strong. Neptune, 30 astronomical units away, is still within this flowing environment, and even Pluto, at its farthest point, has not left the influence of the solar wind. Treating Pluto as the edge of the solar system is like standing on the 3rd block of a city and declaring that the city has ended simply because the buildings in front of you have become shorter. The shape of the heliosphere is not determined by the Sun alone. The solar system is currently traversing the nearby interstellar medium, with external gas and magnetic fields pressing in from the windward side. If the external medium were denser, or if the solar wind were weaker, the heliosphere would shrink. If solar activity increased, the bubble might bulge outward. Astronomers have also observed indirect evidence of similar stellar spheres around other stars, suggesting that stars with stellar winds carve out their own local space within the Milky Way. However, no 2 stars' bubbles are exactly alike. Viewed from the outside, the heliosphere might resemble an irregular, transparent water droplet. The end facing the direction of the solar system's motion is flatter, while the sides are stretched by magnetic fields. Whether there is a long, continuous tail behind it remains a subject of research. Early models tended to depict it as a neat comet-like shape, but later data from missions such as Voyager and IBEX revealed that the actual boundary is far more complex than textbook illustrations suggest. Magnetic fields, temporal variations, and local turbulence can all distort simple contours into irregular structures. NASA's IBEX mission by observing high-energy neutral atoms reflected from the edge, discovered an unusually bright band-like structure in space. These particles were originally charged ions that became neutral atoms after exchanging charges at the heliosphere's edge, then traveled in a straight line back toward the inner solar system. Like messengers sent from afar, they allow scientists to take an indirect snapshot of the heliosphere when they cannot venture outside it. This band-like structure suggests that the relationship between the external interstellar magnetic field and the heliosphere boundary is closer than previously thought. After traveling billions of kilometers outward, the solar wind does not maintain its high speed indefinitely. The external interstellar medium also possesses its own plasma, magnetic fields, and pressure. When these two environments collide head-on, the solar wind is forced to slow down, compress, and change direction. The first major boundary is called the termination shock, located at approximately 80 to 100 astronomical units, though its position shifts with solar activity cycles and changes in the external environment. The termination shock is not a solid wall. It is more like a high-speed river suddenly encountering a countercurrent. The flow does not stop, but instead becomes turbulent, heats up, and flows laterally around the obstacle. After crossing the termination shock, the solar wind enters the heliosheath. The particles here still originate from the Sun, but they have been compressed by the interstellar medium into a slower, hotter, and more irregular flow. The solar sheath is a vast and turbulent buffer zone that can extend up to several tens of astronomical units in width. Temperatures in the heliosheath are high, but high temperature has a different meaning in space. The particles move very fast, and by physical definition, the temperature may reach hundreds of thousands or even millions of degrees. However, their density is extremely low, so there are hardly enough particles to transfer heat to an object. A spacecraft not exposed to sunlight would still cool down as it radiates heat into space. Describing the solar sheath as a searing sea of fire would be misleading. It is more like a high-energy fog composed of extremely SIBO particles. The numbers are high, but the sensation is completely different. Magnetic reconnection also occurs near the boundary. Magnetic field lines from the Sun and interstellar space are stretched, twisted, and, under the right conditions, reconnect, releasing stored magnetic energy in the form of particle acceleration and heating. Magnetic reconnection in Earth's magnetosphere triggers auroras and geomagnetic storms. At the edge of the heliosphere, the same physics occurs on a scale of hundreds of millions of kilometers. The seemingly quiet outer shell of the solar system is, in fact, a plasma front, where energy is constantly exchanged. The locations of the termination shocks are not exactly the same. Voyager 1 and Voyager 2 cross them in different directions, with a distance difference of about 10 astronomical units, nearly 1.5 billion kilometers. This is not an instrument error, but rather an asymmetry in the heliosphere caused by compression from the external environment. We often draw concentric circles to help understand the solar system, but the actual outer layers are more like a balloon skewed by a crosswind. The same boundary lies at different distances from the Sun, depending on the direction of observation. Voyager 1 and Voyager 2 are the only two spacecraft humanity has ever sent to traverse this region. Launched in 1977 during a rare planetary alignment, they were originally intended only to conduct close-up observations of Jupiter, Saturn, Uranus, and Neptune. More than 40 years later, these two machines, far simpler than modern cell phones, are still flying outward, extending their instruments into the plasma frontier where no spacecraft has ever ventured before. Voyager 1 crossed the termination shock in 2004, while Voyager 2 reached a similar region in 2007. The difference in the distances of these two crossings indicates that the heliosphere is not spherical. Voyager 1 traveled closer to the windward side of the heliosphere, while Voyager 2 departed from the opposite side. Attempting to map the shape of the entire solar bubble using just two measurement points is like placing two weather stations in the Pacific Ocean and then trying to predict storms across the entire ocean. Yet the data brought back by the two probes was already astonishing. They discovered that near the boundary, the solar wind slows to the point where there is almost no radial outflow, and particles are forced into lateral flow. Cosmic rays from the Milky Way gradually increase, and the strength and direction of the magnetic field undergo constant and complex changes. The outer shell of the solar system is not a straight contour, but a front that is breathing, undulating, and constantly being squeezed by the external environment. As Voyager 1 approached the edge, scientists observed a strange transitional state. The outward flow of the solar wind had almost vanished, with some particles moving back and forth along magnetic field lines, while cosmic rays from outside had not yet fully reached interstellar levels. Initially, some referred to this region as a magnetic highway, because charged particles appeared to travel along newly formed magnetic channels. Later, researchers more cautiously regarded it as part of the complex structure near the boundary, rather than a simple, ubiquitous corridor. The reason the 2012 crossing was confirmed so late was precisely because the boundary did not provide clear markers like those found on a map. Voyager 1 first observed a sharp drop in solar origin particles and an increase in galactic cosmic rays, but the magnetic field direction did not rotate as clearly as expected. The debate continued for months. It was not until a shock wave generated by a solar eruption reached the probe, causing oscillations in the surrounding plasma, that scientists were able to infer a higher particle density from the oscillation frequency and confirm that the spacecraft had entered interstellar space. Voyager 2's experience was different. When it crossed the heliopause in 2018, its instruments were still able to directly measure the solar wind plasma, providing a set of key data that Voyager 1 lacked. It observed a sharp decrease in solar wind flux, an increase in interstellar cosmic rays, the emergence of an external plasma environment, and different changes in the magnetic field. The details revealed by these two crossings in different directions are not entirely identical. Rather, they demonstrate that the boundary is a dynamic structure, with no single simple scenario that can be replicated at every location. These differences also remind us not to view the trajectories of these two probes as a complete picture of the solar system. The three-dimensional structure of the heliosphere spans hundreds of astronomical units, and the Voyagers merely pierced it with pinprick-sized observation lines from two narrow directions. Their greatness lies not in having mapped the entire landscape for us, but in having shown us for the first time that the map is far more complex than we originally thought. Only when multiple probes fly in different directions in the future will humanity be able to truly measure the nose, flanks, and tail of this solar bubble. In 2012, Voyager 1 crossed the heliopause. In 2018, Voyager 2 also completed this crossing. The heliopause is the boundary between the plasma dominated by the solar wind and the interstellar medium. There, the continuous stream of particles from the Sun can no longer push outward, and the external interstellar plasma begins to gain the upper hand. The media often describe this moment as the Voyagers leaving the solar system. This statement is both correct and incomplete. If we define the solar system as a magnetic bubble blown out by the solar wind, the Voyager probes have indeed entered interstellar space. The plasma surrounding them comes primarily from the interstellar medium, rather than the solar wind. The intensity of cosmic rays is also higher than it is deep within the heliosphere. For the first time, human-made objects have directly experienced the particle shower of interstellar space, and for the first time, we have measured the temperature, density, and magnetic fields of our galactic neighborhood beyond the solar wind. Yet the Sun's gravity does not stop at the heliopause. The Sun still dominates the Voyager's orbits, still tugs at distant comets, and still exerts a faint but persistent gravitational influence on regions far beyond the heliopause. Crossing the heliopause means leaving the realm of the solar wind. It does not mean escaping the Sun's gravitational domain. This is where the solar system is most easily misunderstood. There are several physical boundaries, each ending at a different distance. Beyond the heliopause, too, there is not a true void. The solar system is passing through a portion of the local interstellar cloud, a thin mixture of hydrogen, helium, dust, and charged particles. Its density is far lower than the vacuum standards in Earth's laboratories, yet it is sufficient to suppress the solar wind on a scale of billions of kilometers. Interstellar space is not a black backdrop. It has temperature, magnetic fields, and flow, and carries high-energy particles from distant supernovae. The interstellar plasma density, measured by the Voyager probes, was much higher than in certain regions within the heliosphere. Scientists used disturbances caused by solar flares to excite oscillations in the plasma. By analyzing the oscillation frequencies, they inferred the surrounding particle density and confirmed that the environment around Voyager 1 had changed. It was an extraordinarily quiet moment of proof. No camera captured the spacecraft breaking through the barrier. No metal hull emitted a loud crash. Only a set of frequencies told humanity that we had crossed into a region dominated by a different medium. The size of the heliosphere also varies. Solar activity waxes and wanes over an approximately 11-year cycle. As the Sun's magnetic field reverses, the pressure of the solar wind changes accordingly. When the Sun is active, the bubble may expand farther outward. When it is quiet, external interstellar pressure pushes it back. The boundary is not a fixed ring, but rather resembles a lung that expands and contracts slightly with each breath. What the Voyagers recorded was the boundary they crossed in that particular year, in that specific direction, and under those particular solar conditions, not an unchanging cosmic coordinate. Humans often view the heliosphere as an abstract concept, but it is not far removed from life on Earth. Its magnetic field and solar wind deflect some of the lower energy galactic cosmic rays, reducing the number of particles entering the inner solar system. Cosmic rays still penetrate Earth's atmosphere and create particle cascades at high altitudes, and they also affect spacecraft and astronauts. Without this massive bubble, the radiation environment around Earth would be different. The Sun not only sustains life with light and heat, but also shapes our experience of the Milky Way through an invisible magnetic shell. However, the heliopause is still only about 3 times the distance to Pluto. In terms of the true extent of the Sun's gravitational reach, it does not even count as the endpoint. To continue searching for more distant boundaries, one must leave the flat plane of planetary orbits and enter a spherical shell of ice that nearly envelops the entire solar system. It is called the Oort Cloud. The Oort Cloud has never been directly photographed. It is too far away, and the icy bodies within it are too small and too dim. The sunlight they reflect back to Earth is so faint that it is almost indistinguishable from the background. Its existence is primarily inferred from a more indirect form of evidence, long-period comets. These comets suddenly enter the inner solar system from almost any direction, swing around the Sun, and then vanish into the far reaches of space. Their orbits cannot be explained by the Kuiper Belt alone. Scientists believe the Oort Cloud is a vast spherical reservoir of comets. Its inner edge may lie beyond several thousand astronomical units, while its outer edge could extend to about 100,000 astronomical units, roughly 1.6 light-years. These numbers may sound like a string of zeros, but their true scale becomes apparent when put into perspective. Pluto is, on average, about 40 astronomical units from the Sun, while the outer edge of the Oort Cloud is more than 2,000 times farther away. Light takes only a few hours to travel from the Sun to Pluto, but more than a year and a half to reach the outer edge of the Oort Cloud. The extent of the Oort Cloud can only be understood as an estimate, not a hard-defined boundary captured in images. Different dynamical models yield variations in the inner and outer boundaries, as there is no row of bright celestial bodies there to serve as a reference. It is more like a mist inferred from orbital statistics. What we observe are comets occasionally flung into the inner solar system, and by tracing their trajectories backward, we deduce where those comets once came from. A typical long-period comet moves extremely slowly at its aphelion. Located tens of thousands of astronomical units from the Sun, its speed may be so low that it is almost imperceptible to human intuition. As it falls inward, the Sun's gravity converts potential energy into velocity, and by the time it passes Jupiter's orbit, it has become a high-speed visitor. The bright cometary tail we see in the night sky is usually just the briefest moment in this icy body's long journey. It lingers near the Sun for a few months, but it takes tens of thousands of years to return to the outer reaches of the solar system. Halley's Comet is not a typical long-period comet from the Oort Cloud. Its orbital period is about 76 years, and its orbit has been repeatedly altered by the planets. But it helps us understand the timescale. Halley last passed near Earth in 1986, and it will do so again in 2061. The intervals between visits by Oort Cloud comets are hundreds or even thousands of times longer. If a comet last approached the Sun while Neanderthals were still roaming Eurasia, no calendar could truly predict what human society will look like by the time it returns. The gas and dust that comets eject as they approach the Sun also slightly alter their orbits. Each close flyby is like a small engine firing irregularly, causing the comet to deviate from its original path. Combined with gravitational scattering from planets like Jupiter and Saturn, a comet originally from the Oort Cloud may be captured as a short-period comet, or it may be completely ejected from the solar system. The Oort Cloud is not merely a warehouse that supplies material inward. It is also an exit through which the solar system continuously loses members. If the 1.5 million kilometers from Earth to the Sun were scaled down to 1 meter, Pluto would be about 40 meters away, and the point where Voyager crossed the heliopause would be 120 meters away. The inner edge of the Oort Cloud would lie 5 kilometers away, while its outer edge would be 100 kilometers away. Standing next to the Sun, Pluto would still look like a marker on a street corner. Yet the Oort Cloud would already extend beyond another city. The true volume of the solar system is not determined by the planetary disk, but by a layer of icy outlying regions so sparse as to be nearly invisible. Kepler's laws also push the time scale of this outer region beyond human intuition. For an object orbiting the Sun on a scale of 100,000 astronomical units, a single orbit can take tens of millions of years. When it last passed through perihelion, the positions of Earth's continents, its climate, and the forms of life on it may have been completely different. By the time it returns, the solar system itself will have traveled a great distance along the Milky Way's orbit. The years of the Oort Cloud's inhabitants are not measured by a calendar that a civilization could wait for, but by a clock shared by geology and the Milky Way. The reason the Oort Cloud is roughly spherical is that its objects are no longer governed solely by the plane of the planets. During the early formation of the solar system, the powerful gravity of Jupiter and Saturn scattered a vast number of icy small bodies outward. Some were completely ejected from the solar system, becoming interstellar wanderers. Others were sent into extremely distant elliptical orbits. There, close encounters with neighboring stars, the gravitational tides of the Milky Way as a whole, and perturbations left by the Sun's birth cluster gradually disrupt the direction of their orbits. Galactic tides may sound like the ebb and flow of ocean tides, but they actually stem from slight variations in the Milky Way's gravitational pull at different locations. The Sun and a distant comet are not subjected to exactly the same galactic gravitational pull. While these differences are negligible at close range in the outer regions of the Oort Cloud over an extremely long period of time, these minute variations are sufficient to slowly alter the direction and eccentricity of a comet's orbit. The outermost members of the solar system do not merely orbit the Sun, they also exist within the larger-scale gravitational field of the Milky Way. The influence of a passing star is more like a fleeting nudge. Stars in the Milky Way are widely spaced, but as the Sun orbits the galaxy over hundreds of millions of years, it continually encounters different neighbors. Some pass by from relatively far away, causing only slight perturbations to the Oort Cloud. A very small number of close flybys may increase the number of comets entering the inner solar system hundreds of thousands to millions of years later. This is not because the star directly flings comets toward Earth, but rather because it first gently nudges their distant orbits, and the Sun then takes a very long time to complete the remaining descent. This gives the outer reaches of the solar system a sense of time lag. A stellar encounter might have occurred hundreds of thousands of years ago, yet the comets actually delivered to the inner solar system are only appearing today. When humans see a comet's tail suddenly streaking across the night sky, the cause may lie in an ancient stellar encounter that no living being witnessed. Causal relationships in the universe often unfold in this slow manner: a slight nudge, a long wait, and finally a manifestation in the sky. Over hundreds of millions or even billions of years, these fragments of ice, originally from the planetary plane, have been redistributed in all directions. They continue to orbit the Sun, yet they are not neatly arranged on a single plane like the planets. The Oort Cloud is not a spherical wall packed with comets. It is more like an extremely sparse swarm of bees. Individual objects may be far apart, but their total number may run into the trillions. This sparseness is key to understanding the Oort Cloud. If you were standing on one of these typical icy bodies, you would likely see no magnificent wall of countless companions surrounding you. The Sun is merely a star slightly brighter than others, and nearby icy bodies may be separated by billions or even hundreds of billions of kilometers. Statistically, the Oort Cloud is a vast structure, yet locally it feels like almost complete solitude. It resembles a ghost town larger than a continent, where residents are separated from one another by the distance of several cities. We call it a cloud, not because it resembles the visible, clumpy water vapor in Earth's sky, but because, on the scale of the solar system, the orbits of celestial bodies form a diffusely distributed layer. Real clouds have edges, variations in density, and weather. The Oort Cloud also has an inner and outer structure, though any changes there occur on a time scale of millions of years. There is no sound of wind there, but there are galactic tides. There is no rain, but comets are slowly swept toward the sun. The largest objects in the Oort Cloud may be as big as mountain ranges, and there may even be larger, dwarf planet-sized bodies, but we currently lack a direct census of them. They are too distant and too faint. The sunlight they reflect is so weak that modern telescopes struggle to distinguish them from the background. To actually observe the Oort Cloud directly, we would need a survey far more sensitive than anything available today, or a probe to fly into that region itself. So far, humanity has only seen the occasional ice fragments falling from the cloud. Occasionally, a passing star or a slight tug from the Milky Way's tidal forces will alter the orbit of one of these icy bodies. Originally orbiting slowly tens of thousands of astronomical units away, it is suddenly pushed closer to the Sun. Tens of thousands of years later, it begins to descend, accelerating rapidly as the Sun heats the volatiles on its surface, causing the ice to sublimate into gas and trail a bright cometary tail. When people on Earth look up and see a suddenly appearing comet, the cause may lie in an almost imperceptible gravitational nudge at the edge of the solar system. Long-period comets are messengers from the outer reaches of the solar system. Their orbital periods can span tens of thousands, hundreds of thousands, or even more years. When they first pass near the Sun, they carry volatiles and dust older than Earth's surface. By the time they return, human civilization, coastlines, and even species may have changed. A comet's tail lingers in the night sky for only a few weeks or months, yet it carries material from the solar system's most distant storehouse. The Oort Cloud also explains why the edge of the solar system is never a stable boundary. The farther out one goes, the weaker the Sun's gravity becomes, and the more significant the effects of galactic tides and other stars become. At the very outer reaches, a comet may still nominally orbit the Sun, but its orbit is as fragile as a kite held by two hands at once. A close pass by a nearby star could pull it away or send it back into the inner solar system. The Sun does not remain stationary within the Milky Way. It orbits the galactic center at a speed of over 200 kilometers per second, carrying with it all the planets, Kuiper Belt objects, and members of the Oort Cloud, completing one full orbit in approximately 200 million years. We tend to think of the solar system as a glass sphere fixed in space, but in reality, it is more like a ship sailing through a thin interstellar ocean. The bubble of gas surrounding the ship is constantly shifting. The ice fragments in its wake are tugged by tidal forces, and every passing star nearby may cause the deck to sway ever so slightly. The nearest star, Proxima Centauri, is about 4.24 light-years from the Sun. The outer edge of the Oort Cloud lies about 1.6 light-years away, and it has already extended quite far into this region. In other words, from a gravitational perspective, the solar system is not a tiny isolated island. It has extended a transparent hand almost all the way toward the nearest star. But this hand is not a solid boundary. Rather, it is a gradually thinning zone of influence. The farther out one goes, the harder it is for the sun to determine the fate of objects on its own. If a beam of light were to travel from the sun, it would take just over 8 minutes to reach Earth, about 5.5 hours to reach Pluto, but more than a year to reach the outer edge of the Oort Cloud. If some visible change were to occur on the sun at this very moment, the icy bodies at the outer edge would not know about it for about a year and a half. The solar system is not a synchronized room, but a structure where information delays grow ever longer. For the members of the Oort Cloud, the sun's weather is already old news. The analogy becomes even harsher when we consider sound. Since sound cannot travel in a vacuum, the solar system truly relies on light and radio waves. Even if there were no technical limitations whatsoever, it would take several years to receive a round-trip response after Earth sends a command to a comet in the Oort Cloud. While humans can control lunar missions in real time, Mars missions already face delays, ranging from several minutes to tens of minutes. Missions to the Oort Cloud will inevitably require probes to make their own decisions during long periods of darkness. Flying to the edge of the solar system has never been an ordinary deep space journey. It took New Horizons 9 years to reach Pluto. Traveling at a similar speed toward the inner edge of the Oort Cloud, 10,000 astronomical units away, would take hundreds of years or even longer. To reach the outer edge, a Voyager-class spacecraft would require tens of thousands of years. The solar system may appear to be a familiar stage where planets orbit a star, but its true scale has long since entered a realm of deep time that the lifespan of any civilization cannot easily encompass. From the perspective of travel speed, this scale is even more stark. The Voyager probes have been flying for nearly half a century, yet they have traveled less than 1,000th of a light year. After crossing the heliopause and entering interstellar space, it will still take tens of thousands of years for them to traverse the Oort Cloud. Humanity's first interstellar probes are, in fact, still traveling within the long afterglow of the sun's gravity. They may seem to have left home, but in reality, they are still in the farthest woodlands of the family estate. This gives the term interstellar space 2 distinct meanings. From the perspectives of engineering and plasma physics, the Voyagers are already in interstellar space, as their surroundings are no longer dominated by the solar wind. Dynamically, however, they have not yet truly left the solar system, because the sun still controls their long-term orbits. It is precisely because language packs 2 different scales into a single word that many people mistakenly believe there can be only one boundary. Further out, the sun's gravity interacts with that of neighboring stars and the Milky Way. Astronomers often use the heliosphere or tidal radius to describe the approximate distance over which a star can gravitationally confine a region within the context of the Milky Way's gravity. But this is not a wall. It depends on the sun's position within the Milky Way, the motions of nearby stars, and the specific orbits of celestial bodies. The boundary is more like the area where the shoreline meets the tide. The grains of sand that remain here today may be carried elsewhere tomorrow. This means there are at least 3 honest answers to the question, where is the edge of the solar system? If you're concerned with the major planets, the Kuiper Belt beyond Neptune already belongs to the outer solar system. If you're concerned with the solar wind and magnetic field, the heliopause lies at about 100 astronomical units. If you're concerned with whether the sun can pull objects back over the long term, the answer extends to the Oort Cloud and the more diffuse tidal sphere. All three maps are correct. They simply answer three different questions. Living on Earth, we're accustomed to thinking of boundaries as lines, national borders, coastlines, and the walls of a room. Boundaries in the universe are more like colors blending gradually. Sunlight does not stop at any particular point. The sun's gravitational pull does not suddenly drop to zero, and the solar wind does not vanish simultaneously in all directions. Different forces decay at different rates, and the distances at which they encounter the external environment also vary. Compressing them into a single outer boundary actually obscures the truly fascinating structure of the solar system. From this perspective, the solar system more closely resembles a set of concentric yet irregular spheres of influence. The innermost region is dominated by intense solar radiation and planetary magnetic fields. Just beyond lies the gravitational arena of the giant planets and icy minor bodies. Further out is the heliosphere, where the solar wind and interstellar medium compress against one another. And at the very outer edge is the Oort Cloud, contested by the Sun, the Milky Way, and passing stars. We do not live at the center of a single circle on a map, but rather at the center of overlapping ripples spanning many scales. This hierarchical structure also explains why different space agencies use different terminology to describe the Voyager's location. Solar physicists say they have entered interstellar space because the probes have crossed the heliopause. Planetary dynamists emphasize that they remain within the Sun's gravitational influence. Engineers see spacecraft that are growing increasingly distant from Earth, with their signals growing fainter. No one is playing word games. Everyone is simply defining departure based on different physical mechanisms. When a star passes near the Sun, it does not need to come close to a planet to have an effect. For Earth and Jupiter, its gravitational influence is negligible. For a comet tens of thousands of astronomical units away, however, a tiny gravitational pull, accumulated over an extremely long period, is sufficient to alter its orbit. The outer reaches of the solar system are therefore not a closed box. It loses comets and receives material ejected from other stellar systems, continuously exchanging debris with the Milky Way. Interstellar dust also constantly passes through the solar system. It originates from the winds of other stars, supernova remnants, the remnants of protoplanetary disks, and may even come from comet fragments ejected from other systems long ago. Most particles are too small to be noticed individually, yet they leave tiny impact marks when they strike spacecraft at high speeds. The solar system is not a glass box isolated from the outside world. It is constantly inhaling and exhaling galactic material. The local interstellar environment through which the Sun travels is also subject to change. The Milky Way is not a space uniformly filled with gas. Some regions are thin, gas-free voids blown out by ancient supernovae, while others contain denser, colder clouds. If the Sun were to enter a denser interstellar cloud in the future, external pressure might compress the heliosphere. If it were to enter a rarer region, the solar wind bubble might expand. Planetary orbits will not change immediately as a result, but the cosmic ray environment facing Earth and the size of the solar system's outer envelope may differ from what they are today. This is weather on a massive scale. Earth's weather is measured in days and seasons. Solar activity fluctuates in 11-year cycles. The heliosphere responds to these changes with a delay, and the Sun's passage through different interstellar clouds may take tens of thousands of years or even longer. Different timescales turn like multiple layers of gears rotating simultaneously. The heliosphere we observe is simply the result of these gears having turned to their current positions. Humankind is already learning how to observe this galactic weather. Ground-based telescopes measure interstellar gas through the absorption spectra of nearby stars. Space missions record high-energy neutral atoms and cosmic rays, and the Voyager probes directly sample the plasma. Each instrument can see only a part of the picture. Telescopes see far but indirectly, while probes see close up but from a single path. Only by combining these observations are scientists beginning to understand what the ocean beyond the solar bubble actually looks like. Interstellar objects discovered in recent years are reminding us that this exchange is not purely theoretical. Oumuamua, which appeared in 2017 and traversed the solar system on a hyperbolic orbit, demonstrated that it did not belong to the family bound by the Sun's gravity. Comet Borisov, observed in 2019, exhibited more typical cometary activity. Though they were merely fleeting visitors, they proved that star systems are not entirely isolated from one another. Countless fragments of ice and rock ejected from planets may be drifting through the Milky Way, traveling from one stellar neighborhood to another over hundreds of millions of years. Oumuamua's shape, variations in brightness, and non-gravitational acceleration have sparked a great deal of speculation, but the available evidence is insufficient to classify it as any kind of artificial object. Its true value lies in the fact that it compels astronomers to seriously prepare for the next interstellar visitor. Future survey telescopes will detect such high-speed visitors earlier, and mission concepts are being studied to determine how to rapidly alter orbits to catch up with them. Each visitor is like a small sample sent from another star system, only the envelope is traveling too fast. Borisov, however, makes this interstellar exchange seem simpler and more real. It has a cometary head and tail, releases volatiles, and shares both similarities and differences in chemical composition with comets in our solar system. It tells us that the fundamental physics of comet formation may be just as common in other star systems, while the temperature, chemistry, and planetary history of each system will leave its own unique imprint. The edge of our solar system is not the final page of a self-contained story, but rather the spine of a book through which material is exchanged with the stories of other stars. If a future probe were able to intercept an interstellar object just entering the solar system, it would provide more direct insights than gazing at distant exoplanets. Scientists could measure the composition of dust, the isotopes in ice, complex organic compounds, and magnetic particles to determine the temperatures and radiation experienced by the protoplanetary disk around another star. This would transform interstellar space from merely the void between two stars into a material conduit connecting different worlds. Such visitors have also changed the way we view the Oort Cloud. In the past, people often imagined the outer reaches of the solar system as a clean boundary. The solar system ends here, and the Milky Way begins beyond. The reality is more like a river estuary. Here, fragments of the Sun, interstellar dust, foreign small bodies, and magnetic fields all intermingle. No one can draw a permanent line on the water's surface and declare which drop belongs to the river and which has already become part of the ocean. The edge of the solar system will also change over time. In about 5 billion years, as the Sun's core gradually exhausts its hydrogen fuel, it will expand into a red giant. The environment of the inner planets will be completely transformed. As the Sun loses mass, the orbits of the outer bodies will shift outward. By then, the planetary map we know today will no longer be meaningful. The solar wind, the gravitational influence, and the stability of the Oort Cloud will all be recalibrated. Until then, there is still a long period of exploration ahead. After its flyby of Arrokoth, New Horizons continues to fly outward, measuring the dust and particle environment beyond the Kuiper Belt. The radioisotope power sources on the Voyager spacecraft will gradually decay over time, and instruments must be shut down one by one to conserve energy. Eventually, they will stop transmitting data, but the spacecraft will not stop. Losing radio contact does not mean they have reached their final destination. It simply means that human ears can no longer hear the location reports from those two machines. Their future trajectories also reveal a sense of scale. Tens of thousands of years from now, the Voyagers will skim past certain stars, but they will not enter those stars' planetary systems, much less arrive at a world suitable for landing, as depicted in movies. They will simply continue drifting, carrying the golden records, their instrument housings, and the metal crafted by humans in the 1970s, becoming minuscule specks adrift in the Milky Way. The outer reaches of the solar system are not a gateway beyond which the stars immediately appear. Beyond that lies an unimaginably vast expanse of empty space. The scientific community has been exploring concepts for faster, more specialized interstellar probes. With a higher launch velocity, a spacecraft might reach the edge of the heliosphere, about 100 astronomical units away, within a decade or two to several decades, allowing for comparisons of the solar wind, magnetic fields, and cosmic rays from different directions. Actually venturing into the Oort Cloud remains a much more distant prospect, but simply mapping the heliosphere in 3 dimensions would be enough to transform our understanding of the relationship between the Sun and the Milky Way. Such a mission is not merely about satisfying curiosity about just how big the solar system is. Cosmic rays affect the risks of deep space flight. The structure of the heliosphere determines how the solar wind interacts with the galactic environment, and icy bodies in the outer solar system preserve the materials from which planets formed. If humanity one day sends crewed spacecraft to other stars, the interstellar space that Voyager is currently measuring will be the very waters that the first generation of space travelers must traverse. It may appear empty, but in reality it is filled with particles, magnetic fields, radiation, and endless solitude. Measuring these distant frontiers is, in itself, a science that battles the darkness. The positions of planets can be precisely tracked through reflected sunlight, radar, and spacecraft signals. Small Kuiper Belt objects must be identified as faint moving points of light, and the Oort Cloud is almost entirely inaccessible to direct imaging. Astronomers can only wait for a long-period comet to be perturbed and enter the inner solar system, measure its velocity and orbit, and then, much like reconstructing a crime scene, work backward to determine where that distant gravitational force propelled it from. Every newly discovered extreme celestial body alters this reconstruction. How far its perihelion lies from Neptune, how far its aphelion extends, the inclination of its orbital plane, and whether it forms a statistical cluster with other bodies. All these factors influence our understanding of early star clusters, the migration of giant planets and hidden planets. Research into the outer solar system is not like repeating the same experiment in a laboratory. It is more like piecing together a 4.6 billion-year-old case in a vast archive where clues are dropped only occasionally. Improvements in survey capabilities are gradually shedding light on this archive. More sensitive cameras can repeatedly image the same patch of sky, searching for faint point sources moving slowly relative to background stars. Longer observation periods can extend a brief trajectory into a reliable orbit, and infrared telescopes are better suited for detecting cold, faint objects that reflect almost no visible light. If the ninth planet truly exists, it will not be announced based on a single brilliant deduction, but rather by repeatedly observing it until it is singled out from the background. The direct discovery of the Oort Cloud would be even more difficult. An icy body there already receives extremely faint sunlight, and by the time the reflected light reaches Earth, its brightness would be reduced to near invisibility due to attenuation caused by the twofold increase in distance. To see it, we would need not only large telescopes, but also long-term sky surveys, precise measurements of motion, and an understanding of the background dust in the solar system. Humankind can now observe bright galaxies billions of light years away, yet still struggles to make out the sparse ice clouds within a single light year of our own home. The combination of distance, size, and albedo can sometimes be more challenging to deal with than mere distance. This lack of knowledge does not diminish the reality of the Oort Cloud. The nature of air was understood through wind, clouds, and atmospheric pressure long before it was directly sampled, and black holes left evidence through stellar motion and gravitational waves before they were imaged. Science does not merely acknowledge what the eye can see, it also tests whether a model can simultaneously explain many independent phenomena. The nearly isotropic distribution of long-period comets, their orbital energies, and the planetary scattering model collectively provide the rationale for the existence of the Oort Cloud. The outermost edge is therefore both a physical entity and an epistemological boundary. We know there is likely something there, yet we cannot name each feature individually as we do on the Moon's surface. We know the Sun's gravity continues to exert its influence, yet we cannot draw a closed curve that remains constant forever. The closer we get to the edge of the solar system, the larger the blank spaces on the map become, and the more cautious the language of science must be. Bold imagination can point the way, but evidence alone determines which lines can be retained. In the even more distant future, the Sun will leave behind a white dwarf. Its light and solar wind will diminish significantly, the heliosphere may shrink, and galactic tides and passing stars will continue to strip away the outermost members of the Oort Cloud. The solar system will not end in an instant, but rather, like a shoreline after low tide, it will first lose its outermost fragments, then gradually alter its inner orbits, and ultimately become a set of remnants in the Milky Way that is entirely different from what we see today. This future does not imply that today's solar system is fragile or fleeting. On the contrary, it reveals a fundamental truth. Boundaries are not inherent to an object itself, but rather the result of an ongoing negotiation between the object and its environment. The Sun's mass, the intensity of the solar wind, the pressure of the interstellar medium, galactic tides, and the trajectories of neighboring stars collectively determine how far its influence extends at any given time. A stellar system is not a still life set against the darkness, but a constantly evolving network of relationships. Returning to Pluto, we can finally see its place on this map. It is not the last planet, nor is it the solar system's most distant inhabitant, much less a finish line leading to nothingness. It is a geologically active dwarf planet, a member of an ancient icy disk, and a piece of the puzzle that reveals the solar system to be far larger than just 8 planets. Behind it, lie primordial small bodies like Arakoth, lonely worlds like Sedna that have been cast far away, the invisible boundaries of the heliosphere, the interstellar plasma that the Voyager probes are measuring, and perhaps an entire layer of Oort Cloud, comets enveloping the solar system. With every layer we cross, we think we've finally reached the end, only for the next scale to shrink the previous one into the foreground. What this journey has truly changed is not Pluto's place in the classification system, but humanity's definition of home. Earth is merely a rocky planet near the Sun. Pluto is just a resident of the outer ice belt. The heliosphere is merely a bubble inflated by the solar wind in the galactic ocean. And the Oort Cloud is merely a tenuous rim left by the Sun's gravity in a larger context. We do not inhabit a house with clearly defined walls, but rather a realm composed of many overlapping influences. The Voyager probes continue to fly outward. New Horizons continues to traverse the darkness of the Kuiper Belt, and telescopes continue to search for more distant rogue objects and the hypothetical ninth planet. Every new data point is redrawing the outer contours of the solar system. The map will not be complete when we chart the last planet. It will only grow larger with every probe that arrives, every comet that visits, and every anomalous orbit that is measured. Perhaps one day, humanity will launch multiple true interstellar probes in different directions, reaching the heliopause within decades to map the three-dimensional shape of this solar bubble. Perhaps a telescope will directly discover the largest member of the Oort Cloud. Perhaps the ninth planet will emerge from its long darkness. Each discovery will answer a question and push the boundary out a little further. And tonight, Pluto continues to orbit the Sun. Its ice fields shift slowly in the faint sunlight, accompanied by distant Charon, from which the Sun appears as nothing more than an extraordinarily bright star. Further out lie increasingly sparse fragments of ice, a gradually weakening solar wind, and the growing influence of the Milky Way. Darkness does not begin abruptly, nor does the solar system end suddenly. If we understand the solar system solely in terms of planetary orbits, we reduce our home to a familiar schematic diagram. But if we view it as a region shaped by sunlight, gravity, magnetic fields, icy remnants, and the galactic environment, Pluto transforms from a destination into a milestone. It reminds us that the farthest reaches are often not the edge of the map, but rather the point where the map begins to acknowledge the vast blank spaces that remain. We have always lived in a home without a clear end point. The Sun's light, wind, and gravity extend outward, gradually blending with the Milky Way. Particles, dust, and chance visitors from the Milky Way also constantly flow in. Pluto is not the edge. It is merely the place where humanity once thought it had seen the edge. And every time we take another step toward it, the universe answers, there is still a farther place ahead.